This is heat exchanger part 4. Here we are going to discuss about the logarithmic mean temperature for counterflow heat exchanger. Now we are going to construct a basic shell and tube heat exchanger. Here this is a tube, center tube, through which the cold fluid flows over through this tube, and this tube is enclosed in a shell through which the hot fluids flows over. Okay. Now through this tube the cold fluid is small tc, and at the outlet side this is small th. Okay, this is inlet side, inlet, and this is outlet. This is 1 notated as 1, this is noted as 2. Here the cold fluid passes from the left end to right end. As the name indicates, the counterflow heat exchanger, that means that two fluids are flowing in opposite direction. That means in this case the hot fluid will pass through in this direction, in opposite direction. Okay. In parallel flow heat exchanger, both the fluids are flowing in the same direction, but for counterflow heat exchanger, both the fluids are flowing in the opposite direction. Okay, hence this is a capital TH and this is a capital TC. This capital TH should have the high temperature when compared to capital TC. Now we are going to draw the graph plot for the temperature area plot for the counterflow heat exchanger. Now this is the inlet side and this is the outlet side. This is the length or varying area. Here the cross section is same. If the length changes, the area also should be changing. This is the temperature. This is 1, 2, or at 1 x is equal to 0, at 2 x is equal to L. Okay. Now, first of all, we consider about the flow of hot fluid. In case of the hot fluid, the temperature will be high. That means the temperature will be high at the inlet side. That means somewhere here the TH is very high. That means if flows along the length, the temperature goes on decreasing due to the exchange of heat between the hot fluid versus the cold fluid. Hence, if it is flows in this direction, if the length goes on increasing, this is the direction. Here TH, this is TC, capital TH and capital TC. At the same time, for the cold fluid, this is a very low temperature TC, small tc. And if the length goes on increasing, the temperature goes on increasing due to the gaining of heat from the hot fluid. That means the direction sense, if the length goes on increasing, the temperature goes on increasing. Here this is small tc. Sorry, small th. Now, at the inlet side, by considering the cold fluid, this is a delta T. Delta T at the inlet, that means 1. Here, this is a delta T at outlet. delta T2. Here you can see for case of the counterflow, delta T1 will be equal to capital TC minus small tc. While considering at the outlet, delta T2 is equal to capital TH minus small th. Okay, this is very important. As we know, we are going to analyze about the heat exchanging along the heat exchanger. For that case, we are now just considering about a small area as previous case of the in parallel flow heat exchanger. Now we are considering about this dA, hence we are going to analyze about this area. This is the delta T. Okay, here this is the capital T, this is a small t. Delta T means the capital T minus dt minus small dt. While considering the hot fluid, this is a dt, capital dt, sorry, differential of hot fluid. While considering this fluid, here it is T small t. Here you can see in both cases the Q goes on decreasing, or Q goes on decreasing when considering about the length. Okay, here in this counterflow heat exchanger, the direction also in opposite direction. Here you can see this is a direction of the hot fluid, this is the direction of the cold fluid. This is both are in opposite direction. And another case, for the hot fluid, the heat is losing from the surface. Okay, losing from the fluid. Hence, it is a minus Q. And in the another case, in the direction in case of the cold fluid, in the direction sense, it is in the opposite direction of the hot fluid. Hence, in cold fluid also a negative sign will comes in case of for denoting the direction. As we know, del Q is equal to UA into TH minus TC, or we can able to say U overall heat transfer coefficient into area of effective area of heat exchanging into delta T. This is mean. Now, as per the energy balance equation, we know that the heat lost by the cold fluid, heat lost by the hot fluid should be equal to the heat gained by the cold fluid. By the energy balance equation, del Q is equal to minus, that means the minus of the hot fluid means the heat is going from this fluid, minus m dot h into Cph, that means the specific heat capacity of the hot fluid, into change in temperature of along the particular length. This is a particular length. Similarly, this Q is same for the for the cold fluid too. This minus indicates due to the change in direction, minus m dot mass flow rate of the cold fluid into specific heat capacity of the cold fluid into change in temperature. As we know from this equation, d capital T equal to minus del Q by Ch, and d small t is equal to minus del Q by Cc. This is equal total specific heat capacity of the hot fluid. This is a total specific heat capacity for the cold fluid. Differential of the capital T minus differential of small t, we can able to write it as minus del Q into 1 by Ch minus 1 by Cc is equal to U into dA. That means here only variable is area, minus U into area into capital TH minus small tc into 1 by Ch minus 1 by Cc. Here we can able to this time as the d delta T, capital delta T. The derivation is also same as the previous case for the parallel flow heat exchanger. The small deviation is that much change of sign and varying in the temperature notation. Here from this previous case, and differential of delta T is equal to minus U dA into delta T. by 1 by Cs minus Cc. This is for the particular area. Now we need to consider about this heat exchange on the whole surface or by considering the whole length, that from inlet to outlet or throughout the length 0 to L, 1 to 2. That means here inlet to outlet along the constraint heat transfer along the length is equal to 1 to 2. That means the 2 is outlet, 1 is the inlet. By rearranging this equation by considering the variable separable form, d of delta T by delta T comes here, is equal to minus u into 1 by Cc minus 1 by Cs minus 1 by Cc. Here only variable is the dA, 1 to 2 of dA. Here the integral of the dt by t is equal to ln delta T2 by delta T1 is equal to minus u 1 by Ch minus 1 by Cc of A. As we know, ln delta T2 by delta T1 is equal to minus UA. By substituting all the equation Th minus Tc and Q, here you can able to see Q is equal to C H into delta T, capital T, or Q is equal to Cc into small delta T. Capital delta T means capital delta Th minus capital delta Tc. Here small delta T means small Th minus small delta Tc. By substituting all these things and rearranging, we will get delta T1 minus delta T out. Here what is delta T1? Here you can able to see capital Th minus small th. Here capital Th minus small th means this is a capital Th and this is a small th. Here delta T2 at the outlet. Okay. Sorry, delta Th minus delta T outlet. Here minus indicates UA into delta T2 minus, by considering this minus 2 in this equation, minus delta T2 minus delta T1. Here delta T2 is capital Th minus small th. Delta T1 is this capital Tc minus small tc. This is the logarithmic mean temperature difference term. That means delta T log ln for counterflow heat exchanger. Here only one variable, only by considering this equation, for parallel flow heat exchanger, okay, for parallel flow heat exchanger, you can see from the graph itself, you can able to see here delta T inlet or 1 equal to capital Th minus small tc. Okay, capital Th minus small tc, and delta T2 equal to capital Tc minus small th, capital Tc minus small th. But in case of counterflow heat exchanger, here delta T1 equal to capital Tc minus small tc, and delta T2 equal to capital Th minus small th. Here T, capital Th and small tc, here capital Tc and small th. Here capital Tc and minus small tc, here capital Th minus small th. It is very, very important. This is the only variation for the counterflow as well as for parallel flow heat exchanger. It is very, we need to determine this very clearly. Now in our data book also the same notation is given for the heat exchanger. You can able to see in the page number 152. In the page number 152, you can able to see from the heat exchanger formula, Q is equal to UA into delta T LM, logarithmic mean temperature difference. For the single pass, that means the single pass heat exchanger. For the parallel flow, we can able to see delta T LM, logarithmic mean temperature difference, is equal to capital T1 minus small t1 minus capital T2 minus small t2. Here the notation for the what is the T1, what is the T2, what is small t1, what is small t2, all these are given in the notation side. Please read it carefully. Similarly, for the case of the counter flow also, it is also mentioned it, capital T1 minus small t2 minus capital T2 minus small t1. It is also given here. Please note it clearly that if any temperature goes on in wrong way, we are taking it a wrong way, all the calculations should be wrong. Be cautious about while taking about these notations. Okay. Now we are going to analyze which heat exchanger is good while considering for during the installation. Now we are considering both the case. Okay. Now we are going to analyze it mathematically. Okay. A simple calculation. Now consider a heat exchanger. This is a parallel flow heat exchanger. Okay. This is for cold fluid and this is for hot fluid. And this is a temperature. This is for length. Now we are going to see about another counterflow heat exchanger. Here hot fluid is flowing in this direction, in this direction, and the cold fluid is flowing in this direction, in opposite direction. Here the both fluids are flowing in same direction. Okay, fluids are flowing in same direction. Here the direction is different. This is for counter flow. This is for parallel flow. A small mathematical analysis. Okay. Now we are taking the temperature of the inlet side as well as outlet side as for the both heat exchangers as the same case. For the parallel flow heat exchanger, the high temperature water is 100 degrees Celsius. After heat exchanging process, its temperature comes to 75 degrees Celsius. In the counter flow also, I am taking the hot water as 100 degrees Celsius and after cooling it is 75 degrees Celsius. Just consider about the temperature. Now, in case of the cold water, the inlet temperature of the cold water in parallel flow is 15 degrees Celsius. Now, after heat exchanging process, it comes to 60 degree. Okay, the heat rises to 60 degree. In similar cases for the counter flow also 15 and here is 60. This is for cold, this is for hot, this is for cold, this is for hot. Now we are going to find out the logarithmic mean LMTD for the counter flow as well as the parallel flow. From the data book, we are going to find out the logarithmic mean temperature difference. Okay, for the parallel flow. As we know, the T1 minus, this is a delta T1. This is a delta T1. This is delta T2. Okay, this is delta T2 for the parallel flow cases. Delta T1 means capital TH minus small tc equal to 100 minus 15 equal to 85 degrees Celsius. Similarly, delta T2 outlet equal to 75 minus 60. 75 minus 60 equal to 15. Now, delta T logarithmic mean temperature equal to delta T1 minus delta T2. Delta T1 means, okay, delta T1 means capital T1 minus small t1. This is capital T1. Okay, this is capital T1 minus small t1 divided by or minus delta 2 means the capital T2 minus small t2 divided by ln delta T1 by delta T2. Here we can see 85 minus 15. That means 70 divided by ln 85 by 15. We will get 70 divided by ln 85 by 15. We will get 40.355. By similar analysis, here for delta T, Lm for counterflow heat exchanger. After considering all these things, this is the delta T1, this is the delta T2, hence this is 100 minus 40 minus here 60 minus 40 divided by ln 60 by 40. Kindly do and check. Okay, will be equal to some nearly 49.32 we will get. That means the LMTD for the counterflow heat exchanger is 49 and LMTD for the parallel flow heat exchanger is comparatively 40.33. That means if you are installing if you need to suggest a good heat exchanger with the same inlet and outlet temperature, we need to go for the counterflow heat exchanger because it is more effective when compared to the parallel flow heat exchanger, and it should have the high heat rate when compared to the parallel flow heat exchanger. That high heat rate means we can able to design it with a very compactable or in less size when compared to parallel flow heat exchanger. Hence, it is a more recommendable, or the cross flow heat exchanger is a more recommendable while during the designing of a heat exchanger. In all the practical application, we are going for this counterflow heat exchanger because it should have the more effectiveness heat transfer efficiency or heat transfer rate. Now we are going